For the last year, I have been working on the next iteration of my humanoid robot. For like 3 months, I designed and manufactured most of the components, and then for the last 9 months, I've been struggling through a bunch of problems with communications between the microcontroller and the sensor chips on the sensor boards in the individual joints. I've read a bunch of things about how to help eliminate noise in wires between components, and I want to do some experimenting today to figure out what are the best arrangements of components to neutralize ringing and noise from the longer cables that I need to connect between knee and ankle and hip to the microcontroller that controls the leg. Look at that floppy signal coming out of an Arduino Nano whenever the pin goes high or low. When we attach a 1 meter ribbon cable to it, the ringing gets even louder. I have a chip that needs good high and low signals on the serial clock in order to send and receive data successfully. It works okay when the cable is really short, but it fails pretty hard when the cable's more than a few inches long. All this ringing is causing major communication problems. Let's test several termination techniques to see which will be best suited to my situation. We'll make a little circuit board that has 7 different terminations. First is our control, a direct connection without any components. Number 2 has a resistor in series. Number 3 has a resistor in parallel. Number 4 has a capacitor in series. Number 5 has a capacitor in parallel. 6 is a resistor in series followed by a capacitor in parallel. And 7 is a resistor and capacitor in parallel. Once we design the circuits, we can manufacture and assemble the circuit board for our little experiment. I love my little basement factory. It's so cool to go from an empty KitKat file to holding something in my hand in under 2 hours. So the way the setup will work is we'll have an Arduino Nano plugged into a breadboard, then we'll take a jumper wire off the breadboard into whichever wire on the ribbon cable we want to play with. On the other side of the ribbon cable is our experiment board. Its exposed pads I can touch with the probe to take measurements. Let's walk through each of these tests and see what kind of results we get. This first one is the control, and you can see zoomed out at a 2 microsecond scale is several pulses from the Arduino. And then on the bottom we have the rising edge and the falling edge from the Arduino, zoomed in much more closely to see the signal quality. The green signal is measured right at the Arduino's output, and the yellow signal is measured at the end of the experiment. Without any components to modify our signal, we can see that it's actually amplified by the time it makes it out to the end of the ribbon cable. With our resistor in series, it actually nullifies all of that bouncing almost entirely. There's a slight rise as the signal goes high and a slight dip when the signal goes low before it stabilizes at the final voltage, but it otherwise completely eliminates all of that noise. It's very impressive. Also, 165 ohms was the lowest resistance surface mount resistor that I had available for the test. So it may even be more pronounced with something like 10 ohms or half an ohm. The resistance of the ribbon cable across 1 meter is half an ohm. With the resistor in parallel, we see almost no effect on the signal. Now granted, this is a 2K ohm resistor, so it's not allowing a lot of current to go through. Perhaps a lower resistance might have muted the noise better, but it would have taken more current. With a capacitor in series, it was actually really interesting. It offsets to where the center of the signal is at ground, and when the signal goes high, it goes from, it flops either side above and below ground instead of being at ground. I think also this is more for high frequency kind of terminations that you would use a series capacitor like this, and probably something more like in the picofarads. It doesn't apply to my situation, but there's definitely situations where this would be useful. With a 10 nanofarad capacitor in parallel, we can see that when the signal tries to go high or go low, it begins to charge or discharge that capacitor. It does take those peaks out, and it does smooth the curve quite a bit. We can see that the sharp square wave gets rounded off at the corners when the signal changes. But it does effectively reduce or eliminate the noise that would cause problems in our circuit. This one with a 1K ohm resistor is probably way too much resistance, and a 100 nanofarad capacitor is probably way too much capacitance for the frequencies we're looking at here. In the zoomed out view, we can see that it's only barely discharging and charging again in between cycles. So with much lower numbers on those components, I suspect that we could see a lot more smoothing happening. And finally, with a resistor in parallel and a capacitor in parallel, we see essentially the same thing that we saw with a capacitor in parallel. If I had chosen a 10 nanofarad capacitor, we would see almost exactly the same graph as we saw for number 5. Okay, so we have a pretty good idea of how to place inline resistors and parallel capacitors to help manage echoing and ringing in our cables. So that's got me curious. Let's go back into my my sensor pad. Let's run it through this longer cable, and let's see what we can see with it actually operating. It has lots of signals running down that ribbon cable that interfere with each other and harmonize with each other. Here's the master clock. This is the serial clock with the cable select. We can look at the serial clock with the data out. Looking at the data out, if we set it to trigger where the data out goes high, why is it triggering right here? This is a weird spot for it. Let's zoom in on that. What is that? Oh my god. Those are my missing ones and zeros. Those are the bits that I've been looking for this whole time. I spent 9 months trying to find this, trying to understand what was going wrong. Oh my god, it was so awful. I gained like 15 pounds. That is such a relief. I'm so happy. Now that we've seen this, and we've done some experiments, and we have different techniques to mitigate the ringing and the echoing that's happening on these longer ribbon cables, I'm going to redesign a controller and a sensor board. I'm Josh Whitman with Whitman Technological. I love science, and I hope you do too.